So without a whole lot more, I will just invite people to mute themselves. I think Carolina will be okay to be interrupted with points of clarification along the way, with the idea that at the end we'll have a discussion and more detailed questions. But I'll let her tell you that as she begins. Thank you very much, Carolina. Go ahead.
Thank you, Chris. Hello, everyone. I would like to say before to start with my talk that it's really a pleasure for me to present today my recent work, and I thank the organizers to giving me this opportunity. And today I will talk about some laboratory experiments that we have recently collected to address the role of fault orientation in earthquake seismic precursors. And I performed this work with Nicolas Brantou at UCL London in the UK. And I would like also to acknowledge some people that in the past years was fundamental in discussing the role of fault orientation in fault reactivation. And I started to work on this topic during my PhD, so quite long ago now. And discussion with these people was fundamental to understand how to deal with this topic, especially in the lab and in rock deformation experiments. And this work is also done with in the framework of my Marie Curie action that is focused on the role of stress history on earthquake potential of faults. This is the outline of the talk I give today. I will start with a brief introduction, during which I will recall some fundamentals of earthquake cycles and fault mechanics that will be helpful to understand and put into context my experiments. Then I will explain you the laboratory approach we have used, and I will move on then to the mechanical data, to the acoustic data, and I will conclude with a few final remarks and implications for natural faults. The simplest model we have in mind when we think about earthquakes is a fault that is embedded in an homogeneous elastic medium. And while the medium is loading by tectonic stress, the fault is locked, but the surrounding medium accumulates elastic energy while deforming. And as soon as the shear stress achieves the strength of the fault, a sudden stress drop occurs. The fault slips and the energy is released, generating an earthquake in the surrounding rock volume. And this repeats over time. And the three main ingredients to have an earthquake then are a stress field evolution that load the fault medium, a brittle rock that can store elastic energy while the loading occurs, and a fault that can slip and release this energy that is accumulated. Keeping in mind these three main ingredients, I will now give you some details about fault mechanics, and in particular how stress is built up on a fault plane. So a fault plane lies at a certain angle to the far field stress that is here indicated by the maximum principal stress and the minimum principal stress. And this far field stress will result in a normal stress and the shear stress acting on a fault. Commonly, we frame fault reactivation in a shear stress versus normal stress plane, where the reactivation can be described by this criterion here that is described by this equation. So the shear stress is equal to a friction coefficient times the normal stress acting on the fault. In the same plot, we can also represent the stress field that the rock undergoes, and we can represent it through a circle. And the minimum and the maximum principal stresses are the points in which the circles intercept the x-axis. while a fault can be represented by a point lying on this circle. And this angle is 2 times the angle between the fault and the maximum principal stress. While loading the fault, the maximum principal stress increases due to the tectonic loading, and the normal stress and the shear stress resolved on the fault increases as well. And this until the stresses on the fault intercepts the reactivation criterion. And the red line that I show here indicates the loading path. And this loading path describes the coupling between the normal stress and the shear stress acting on a fault plane. And this depends on the orientation of the fault. Different fault orientation will result indeed in different slopes of this line. And when thinking about natural earthquakes, fault orientation matters because it has been documented that earthquakes can occur on faults that lie at different orientation to the maximum principal stress. And to show you this, I report here a plot from Collettini and Simpson in which the number of ruptures is indicated against the dip angle of the fault. And according to the Andersonian theory and based on Barley friction, we would expect optimally oriented faults to occur at these orientations here that are 60 degrees dip angle in the case of normal faults and 30 degrees dip angles in the case of reverse faults, as indicated by the red lines. But the distribution of the ruptures show us that earthquakes can occur also in faults that are oriented not at the optimal angle, but also at other orientations. Another important aspect of natural seismicity is that it has been observed before certain main shocks that the number of earthquakes and the seismicity rate increases in the month, 2 days before the main shock. And here I report a plot that was recently published by Kiatek and co-authors, in which they show that before the magnitude 7.8 earthquakes in Turkey, there was an acceleration of the seismicity rate in the 8 months preceding the main shock. And this has been shown also for other earthquakes. And for example, in this case, Bouchon and co-authors show that considering more than one, but different seismic sequences and stacking them together, it can be recognized this pattern for interplate earthquakes. And we can see here the cumulative number of events before the main shock and the abrupt acceleration that occurs in the days before the main shock. These 4 shocks are important for us because understanding when and why they occur will help us in understanding the potential of forecast earthquakes. However, it has been shown in several studies, and here I report this map distribution by Marsan et al. In 2014, they published this distribution map that shows that earthquakes may or may not show this acceleration of the seismic activity before the main shock. And we, as a scientific community, we encounter several difficulties in trying to understand how and when foreshocks occur. It has been shown that it depends on the type of analysis, also the amount of foreshocks that can be detected before main shock. But it has also been shown that this depends on the resolutions that our techniques have in detecting this acceleration in seismic activity. Moreover, another important point is how the background seismicity rate is considered, and how the deviation from the background seismicity rate is taken into consideration. And while reading some literature on the topic, I ended up in reading also this kind of observations. Here, for example, Trugman and Ross wrote, these observations are difficult to reconcile. So the fact that main shock occurs only in less than half, that foreshocks occur in less than half of the main shock worldwide. So they state that these observations are difficult to reconcile with laboratory earthquake experiments and theoretical models of earthquake nucleation, which both suggest that foreshock activity should be nearly ubiquitous. So I asked myself, are foreshocks ubiquitous in the laboratory? Well, from the literature, we know that acoustic emission rate accelerates before main shock. I report here a couple of plots that show this. Some SOCAT experiments performed by Thompson and co-authors show this acceleration of the seismicity rate just before the main shock, but also in other experiments, this is clear. For example, here I report some data from Dresen and co-authors in 2020, where they show that for smooth and rough faults, there are some differences. However, it's always detectable in the lab, an evolution of the cumulative number of events before the main shock. And all these experiments were performed on faults that are well oriented to the maximum principal stress, faults that are at 30 degrees to the maximum principal stress, and in an elastic, in a surrounding rock that can be considered an elastic medium. All these observations together set my key question that I try to address with the talk I'm giving today. Are laboratory seismic precursors influenced by the far-field stress to fault orientation? Or in other words, if we add one more complexity to our simple laboratory system, that is the orientation of the fault, can we reproduce a more complex behavior similar to what we observe in natural faults? I will now show you how in the laboratory we reproduce faults and how we reproduce earthquakes. So the configuration we have used is a triaxial SOCAT configuration in which a sample of rock, in this case granite, is cut at a certain angle to the axis of the sample. In this dataset, we prepared samples at different orientation to the maximum principal stress. So here are here you can see all the angles that we tested from 30 degrees to 70 degrees. And in a triaxial experiment, the minimum principal stress is imposed by a confining medium, in this case is oil, and the axial stress that imposes the deformation is imposed by an axial piston, by a vertical piston at a constant loading rate. The boundary condition for our experiments are 40 MPa of confining pressure, a strain rate about 10 to the minus 6 seconds. As I mentioned before, different orientation to the maximum principal stress. We have also performed one experiment on an intact sample as a baseline to compare our SOCAT experiments. And all the experiments were performed on a granite, a French granite. And the surface finishing was done hand lapping the sample with 120 grit powder that is equivalent to an asperity size of 125 microns. We have equipped our sample with 12 piezoelectric transducers to record acoustic emissions. and also with 5 radial strain gauges and 5 axial strain gauges. And this is the sensor map showing how the sensors are located with respect to our fault plane. Let's move on to the results. I will start showing you our 2 end members that are the intact sample in which a new fracture is produced, and the reactivation of a well-oriented fault. So in blue, we can see the reactivation of a well-oriented fault in a plot showing the differential stress versus the axial displacement. So we can see that after an initial elastic loading, a yield and the rollover of the curve, a steady state constant value is achieved that is controlled by the friction of the socket. On the other hand, we can see that at the same confining pressure to break the rock was necessary to achieve a higher level of stress. And in this case, we can see that the stress initially increased linearly with the axial displacement until the peak strength of the material is achieved and a stress drop occurs. We can visualize this in tau sigma n space using again more circles. And here, the small Moore circle represent the stress necessary to reactivate the fault. So when the fault that is optimally oriented achieves the fault reactivation criterion. And the big Moore circle represents the failure of the intact rock. So that occurs when the circle is tangent to the rock failure criterion. We can now populate our plot with all the other samples that were deformed with the sockets at different orientations. So the sample in which the socket is oriented at 40 degrees to the maximum principal stress show at the beginning behavior that is similar to the well-oriented sample, and a steady state is achieved, but after 2 millimeters of slip, we can see that a stress drop occurs and a stick slip occurs. So stick slip for us in the laboratory are the equivalent of seismic cycles. So these are our laboratory earthquakes. For the 50 degrees sample, we see that the behavior is different from the 30 and the 40, and is stick slip behavior since the very beginning of the deformation of the sample. For the 60 degrees sample, the stress increases up to 420 MPa roughly, and then a stress drop occurs. And also in this case, it's a stick slip because the deformation occurred along the fault surface. 70 degrees sample is misoriented and the fault couldn't reactivate. So in this case, we created a new failure in the sample and a new fracture in the intact rock. So we can again represent the reactivation of faults that are misoriented with a Moore circle in this shear stress versus normal stress space. And we can see that misoriented fault requires differential stress that are higher than the differential stress required to reactivate a well-oriented fault. We can, at the same time, look at the axial and radial strain obtained from strain gauges. In this case, I first show you again the 2 end members behaviors. So in the case of the reactivated fault, we can see that both the axial strain and the radial strain increase linearly with differential stress. On the other hand, when we look at the values for the intact rock sample, we see that the strain increases linearly for the first part of the curve, but then after the yield, it deviates from linearity. And in rock mechanics, this is when it's considered when we have the onset of inelastic deformation in our sample. At this point, we can also visualize this in a stress space, but in this case, we change the stresses that we plot in the two axes. We plot the differential stress and the mean stress, because now we are looking at what the host rock experience in terms of stresses, and not what the fault experience in terms of stresses. And our triaxial SOCAT experiments, they always follow a path in differential stress and mean stress that are as this one that is shown here. And in the disk space, we can define as a criterion the onset of the latency, or also the onset of inelastic deformation. So the material will deform elastically until a critical value will be achieved. And after this value, it will deform inelastically until the strength of the fault, the rock is achieved, and the failure, a new failure occurs. So when we populate these two plots with all the curves that we collected, we can see that while the fault is more and more misoriented, the host rock surrounding the fault undergoes higher and higher differential stress. And for faults that are at 30, 40, and 50 degrees, the behavior in terms of strain is always elastic. So we see that is linearly dependent on stress. However, when we reactivate a fault that is at 60 degrees, we can see that the host rock starts to deform inelastically. And so the host rock is critically stressed. And again, we can visualize this in a stress space. And for example, here I show a 30 degrees sample that would be fully in the elastic field, a fault oriented in our case at, for example, 50 degrees will be still in the elastic field. However, if the fault is oriented at 60 degrees, the sample will be in the inelastic field. Now we can look at the strain partitioning between on-fault and off-fault deformation. In this specific case, in our laboratory experiments, I define on-fault deformation that is accommodated by the fault, and off-fault the deformation that is accommodated by the rock surrounding the fault. That could be, in this case, both elastic and inelastic. And we can measure this strain partitioning considering the displacement sensor that is outside our vessel that measure the bulk deformation. So in the displacement sensor is included both the on-fault and the on-fault. Whereas our strain gauge, they record only the off-fault deformation. So comparing the two values, we can discriminate between the partitioning of the strain of fault and on-fault. And these are the results in our samples where the fault was reactivated. So the strain partitioning that is shown here can go from 0 to 1, where 0 indicates that the deformation is all occurring along the fault plane, and 1 it indicates that the deformation is all occurring in the surrounding rock. During well-oriented fault reactivation, we see when the fault is reactivated in a stable manner, so through stable slip, we see that after an initial high value of strain partitioning. That means that the strain is mainly in the bulk. The strain partitioning gradually decreases until it is all occurring along the fault. And this means that the transition between the deformation accumulated in the bulk and the deformation accumulated along the fault is smooth and progressive. We can recognize the same pattern when looking at the 40 degrees samples. However, when the fault suddenly slips and a stress drop occurs, the following stick slip cycle is characterized by a deformation that is all accommodated in the bulk during the stick phase. And this is what we expect when we have a stick slip in the laboratory. The same we can see for the 50 degrees sample, where stick slip behavior is characterized by a strain partitioning that is almost equal to 1 as a value. That means that all the deformation is stored in the surrounding volume. And also for the 60 degrees sample, that is the most misoriented sample, we see a similar behavior. And we can also have a look at the data in terms of shear stress and normal stress at reactivation. So here I report the experimental data, and the color bar indicates the slip occurring on the fault. So the slip correcting by the strain partitioning value. And for well-oriented faults that mainly creep, we can see that the fault unlocks at friction values of 0.3, and then there's a slip hardening phase until a steady state is achieved for values of friction that are typical of Barrelis friction values. At 50 degrees, the fault is reactivated directly at higher friction values. So there's not a strong slip hardening phase before. And again, the friction is coherent with Barrelis friction. At 60 degrees, the fault is fully locked until it reactivates. And this occurs at slightly lower values than Barrelis friction. But the main reason why I wanted to show you this plot is to show you that the normal stress at which the fault undergoes before reactivation is very different in our experiments. And it goes from a normal stress of 60 degrees for the well-oriented sample up to a normal stress of 360 degrees for the misoriented samples. And this could be also an explanation for the transition that we observed from a smooth and stable sliding behavior to a stick slip behavior with progressively higher and higher stress drop. So now that we have a general idea of the mechanical behavior of our sample, I would like to move on to the acoustic signature. And the first plot I show you is the cumulative acoustic emissions number as a function of time for all our experiments. And I plot also the differential stress as a reference. So it's clear that for the intact sample, the cumulative acoustic emissions are higher in number. And we can also see that the number of acoustic emission increases while misorienting more and more the fault. But
Carolina,
yes.
could I interrupt for just a moment? Would you say a few words, please, about how you're measuring the acoustic emission?
Yes, sure. So acoustic emissions were measured. So this is the sensor map. So we have 12 sensors, and the acoustic emissions are measured by these 12 sensors, and they are located. And so this is the number of acoustic emissions retrieved after the location of the events.
Understood. And are you using some sort of thresholding? Are you using cross correlation? How are you actually extracting the acoustic emission?
Okay, so the acoustic emissions are, yes, something that I didn't say is that the acoustic emissions are recorded continuously at a sampling rate of 50 megahertz. And then for the peaking technique, I think that maybe Nicola can give you a more precise answer, since the peaking was performed by Nicola.
You want me to answer this?
Yes, I think you can have a more precise answer than me, for sure.
So it's continuously recorded, and we have a first detection where I just use a STA, LTA thresholding type detection, and then we do template matching to detect smaller events. So there's a two-stage thing. We have first detection on the continuous waveforms, and then template using all the high-quality events as templates, and we just pass them through to detect more events.
Great.
That
answers the question. Thanks a lot, Nicola.
Okay. Okay, so if we now focus on 3 stick slip cycles at 40, 50, and 60 degrees, and we zoom in, this is what we can see in terms of cumulative acoustic emission evolution with time. So for the 40 degrees socket, we can see that the number abruptly increases right before the stress drop occurs. For the 50 degrees socket, we can see that it starts to increase before, but again, we can recognize this abrupt acceleration while approaching the stress drop. And for the 60 degrees socket, there is an increase in cumulative acoustic emission numbers, but it's somehow missing the exponential increase at the very end before the stress drop. So I recall here the fact that in terms of strain partitioning during all these 3 stick slip cycles, the strain was almost 100% of fault deformation that could be elastic and inelastic. When we look at the location of the events, this is what we see. And at first, I was a bit surprised when I see this result, but in the end, it's not that not intuitive, I would say. Indeed, when we deform at 40 degrees or 50 degrees socket orientation, we have that all our activity is occurring on the plane, and the surrounding rock is still in the elastic domain, so is not illuminated by any acoustic activity. On the other hand, when we reactivate a fault that is so misoriented that the surrounding host rock is critically stressed, we are above the elastic limit of the material, and we start to illuminate also the rock surrounding. So the off fault in this case is stressed above the onset of inelastic deformation. And in this case, the strain that is accommodated by the surrounding rock volume is both elastic and inelastic. And we can also compare
Carolina.
Yes.
Sorry, sure. Can you show again the acceleration of seismicity, the previous slide?
Yeah. This one, right?
Okay, okay. So in the case of the 60 degrees, you have almost a continuous acceleration of seismicity rate production.
Exactly.
Okay, thanks.
And we can compare Also, these locations with events that occurred in the intact sample. And in this case, the number of events is way much higher. But if we stop before, a tiny bit before, at a stress that is comparable with the stress at which the 60 degrees sample reactivated, we can see that the distribution of the events is not that different from the one that we can observe for the misoriented fault. And the next step is to try to understand if there is any precursory activity that happens on the fault. And to do so, we tried to select a volume of rock that is in the surrounding of the fault plane. And in this case, the distance that we have taken is plus or minus 3 millimeters from the fault plane. And we can plot the cumulative acoustic emission number for this volume. And this is the red line that we can see here. And we can compare it with the total one, that is the black, and what we call here the off fault, that is here just what is not happening in this plus or minus 3 millimeters volume. And we see that the off fault has a trend that is very similar to the total one, and that there's not a clear acceleration of the seismic activity when we select the on-fault volume.
Carolina.
Yes.
Joan Gomberg has a question. Joan, go ahead.
Yeah, sure.
Sorry, I had to find my mute button. I have two questions about the previous slide. One is general. Did you look at the amplitudes of the acoustic emissions? Do they also increase consistently with the rate of events? And then the second question is, in the 60-degree case, do the events that occur on the cut as opposed to in the bulk differ in characteristics, for example?
Okay, so I had a look at the amplitude, and the amplitude increases while approaching the stress drop. I didn't do a deep analysis into this. I am planning to do it. But for the moment, I couldn't see any difference between, in amplitude, for example, between events that occurs near the fault or far from the fault.
Okay, thank you.
But in terms of, in terms of amplitude, I might have a slide in the backup slides. We might discuss this later on if you want.
Thank you.
So after sampling this volume that surrounded our fault, we decided to do a small statistical analysis in which we analyzed the volume of acoustic emissions as if we don't know where the fault is. So we sampled the volumes for faults that are oriented at different deep angles. So from, for example, 20 degrees or 30, 40, and so on, always considering a volume of plus and minus 3 millimeters from the fault plane. And we did the same analysis, also changing the deep direction of our fault, because in our reference system, the fault is always dipping at 90 degrees. That is, in this case, toward north, but we could also sample volumes as if the fault is dipping toward other directions. And this is the result of this analysis. So in the plot, we can see the acoustic emission rate normalized by the volume and is color-coded as a function of the deep angle. So each line each line describes the acoustic emission rate for a certain volume in the sample, sampled at a certain dip angle. And in black, I report the acoustic emission rate in the volume where I know that the fault is. So in this case, at 50 degrees, the black line indicates the acoustic emission rate in the volume where the fault is. If, for example, we take a volume for a fault that is oriented at 70 degrees, so higher than the real fault orientation, we see that the acoustic emission rate is lower and lower. So we can see also a gradient with respect to the dip angle somehow. If we do the same analysis, and this is true for each cycle, and we can also see that it tends to accelerate exponentially as we approach the stress drop in all the three cases. If we do the same analysis for the sample containing the very, very misoriented fault, what we can see is that all the sampled volumes tend to give the same acoustic emission rate, and that the acoustic emission rate calculated on the volume containing the fault is not any different from the others. So from this blind analysis, let's say, we couldn't say where the fault that then reactivated really is. And here, as a comparison, I show you also the evolution of the acoustic emission rate for the intact sample that fails, in which we can see that there's a slow increase at the beginning and then an abrupt increase when the sample is approaching the failure. And this slow initial increase is compatible with what we see in the misoriented sample. So we tend to think that this increase in acoustic emission rate that we see in all the sampled volumes is due to the fact that the volume of rock is critically stressed and is approaching the failure. And it's not clear from this analysis if any precursory activity related to the fault that will reactivate is there. And we can also color coded the same curves as a function of dip direction. And we see something that is very similar. So in the 50 degrees case, we can see that as we deviate from the real dip direction of the fault, that in our case is 90 degrees. So as we deviate from 90, the acoustic emission rate lowers down. And again, for the 60 degrees, there's not a clear trend, and all the sampled volumes appear to be the same. And we can also address the spatial distribution of our acoustic emission. So in this case here, I show you the number of events as a function of the distance from the fault plane. And again, I tried also to sample different rock volumes that are differently oriented. In this case, the color coding is showing the change in dip angle. So we can see that for the 50 degrees, there's a localization of the deformation along the fault plane that is not surprising when we, for example, we look back at the locations of the events in the seismic cycles, they appear like this. So it's not surprising that they localize along the fault plane. And we also see that for the fault that is at 50 degrees, the number of the events is maximum with respect to all the other orientations. At 60 degrees, there's again no clear trend, and the number of events is homogeneously distributed throughout the sample. in this case, I have to specify that we sampled a smaller volume than the whole sample volume to keep the volume always constant, so that the number of the events is always consistent and comparable between the different orientations compared in these plots. And if we compare what we see in the 60 degrees samples with what we see in the intact rock sample, we see a similar distribution that is distributed within the rock volume with no clear relation to the fault plane that is existing in the rock. So again, our result shows that there's not clear localization of the seismicity along the fault plane, and the activity that we see is very similar to the one occurring in an intact rock sample that is approaching the failure. And we can do the same small exercise for different deep directions, as I showed you before, and we see something that is similar. So to wrap up the observations that we have done in the laboratory, we observed that misoriented faults are reactivated according to the Coulomb-Moore theory. So we could reactivate until the lockup angle, and then we observed the failure. So we could reactivate up to 60 degrees from the maximum principal stress, and the 70 degrees sample resulted in a new failure occurring in a sample. We could observe a transition from stable creep to unstable behavior stick slip with increasing angle to the maximum principal stress, and we can relate this to the normal stress increase. And also we observe inelastic deformation if the fault is sufficiently misoriented, in our case 60 degrees, as documented both by strain gauges and acoustic emission locations. So the main findings or important outcomes of this study is that we lack of detectable seismic precursors, at least in terms of acoustic emission rate approaching the main event, and a spatial localization of events in the fault surrounding. So somehow we documented that detection of foreshocks in the laboratory is not ubiquitous. So adding some complexities, for example, in our case, is the stress field, the fault orientation interplay gives less predictable behavior. And this is somehow also in agreement with previous laboratory studies that shows, for example, that if we include geometrical complexities and fault roughness, we can also produce a less predictable behavior. And in our case, what I find interesting is that we could also reproduce in the laboratory some background seismicity that in this case comes from the surrounding rock volume that is critically stressed. And this can introduce in our system also some difficulties in trying to see for precursors occurring on fault. And as a final slide, I want to make a question somehow. So what are the implications for natural seismicity? And so this, I think, is also a good starting point for discussion, because, of course, it's always a bit difficult to link laboratory observations to natural observations. But in a way, misoriented faults that lie at high angle to the maximum principal stress are subjected to relatively high normal stresses when compared to other faults at the same depth that are well oriented. So is it a matter of fault orientation or a high normal stress, mean stress, from the point of view of fault and host rock both? And I found that in the literature, there are some correlation that have been observed in terms of fault shock occurrence with the depth or changing faulting type, and they all imply, in terms of interpretations, an important role of the stress. So maybe this could be relevant also for differently oriented faults in complex natural settings. And with this, I conclude. I thank you for your attention, and I am looking forward to discuss with you.
Excellent, Carolina. Thank you very much. I will invite everyone to unmute or otherwise join me in, thank you, Carolina, for a really excellent talk. Yeah, so many interesting things about the data. Okay, so while we're letting Carolina catch her breath for a second, the simplest way for us to operate is to use the reactions button at the bottom of your screen to raise your hand. Thank you, Georg Drazen, for doing that so we can see what it looks like. I assume everyone knows all about this, but yeah, please raise your hand. Please participate in the discussion, especially early career people. Georg.
Carolina, very, very nice talk. Thank you. Now, I have a question. You didn't mention microstructures. Have you looked at the microstructures of the deformed samples? I mean, I would anticipate that with increasing misorientation, you showed this, you partition more and more deformation into the damage zone surrounding the fault and then into the entire rock volume. So I was wondering what the microstructure would say there. Because your location accuracy for acoustic emissions is limited, right? Plus minus 3 millimeters, but there may be something that's happening in there. Also with orientation of the cracks or of the focal mechanisms of the acoustic emissions as you approach the fault.
Yes, so I haven't looked at microstructures yet, but when you look at the sample after the experiment, you can see some wear material on the fault plane at 60 degrees, but you cannot really see a lot of damage outside the sample. And I was also surprised by this outcome because I would have expected to see even by high, more clearly damage in the surrounding rock. For sure, I will check with microstructural observations, but another indication that the rock was not so highly damaged in the surrounding is that the strain gauge values after the stress drop went back almost to the initial value. So it means that there was not permanent or not, let's say, not substantially permanent deformation within the bulk.
Okay, that may depend on the distance of the strain gauge to the fault, though. But
but these strain gauges were located, let's say, these strain gauges were meant to measure more the host rock deformation. So they are not very near the fault, indeed.
And then one final clarification, the 60-degree sample, did that fail or not?
No, it's it reactivated on the SOCAPs.
Okay, thank you very much.
Joan Gomberg, go ahead.
Okay, this will be my last question, I promise. I know you had one slide where you had in the 50-degree sample, you had multiple cycles, and it looked like this one, yes. It looks like, is there some sort of relation between the stress drops in the 50-degree one and the number of emissions? So it looks like as the stress drop increases, the number of emissions decreases. Does that imply that more of the strain release is going into the radiation as opposed to on the fault itself as a slip event? Is there some trade-off between the two?
My interpretation of this as an experimentalist is that the first seismic cycle could be different from the following ones because the fault at the very beginning is just a socket that we artificially prepared, and that they are basically two surfaces that we put together. So probably in the first cycle, the surface can evolve way much more than in the following cycles. So we can see clearly that it is higher for the first cycle than for the following. I think it would be nice to have more cycles to check what you said. The problem is that in this configuration, we are limited by the amount of slip, because if we slip too much, the jacket breaks and the oil goes in the sample. So for example, in the 60 degrees, it would have been nice to have a second stick slip, but we couldn't again for these like experimental limitations, I would say, because one single stress drop produced something like 5 millimeters of slip along the socket. That for our samples is a lot. So we couldn't go farther.
Okay, thank you.
Carolina, fabulous talk. Really enjoyed that. Lots of interesting stuff. And before I ask my question, I want to encourage everyone to participate. So please raise your hand and join. Carolina, one of your conclusions was that foreshocks are not ubiquitous, especially for, let's say, misoriented faults. So maybe I have first a point of clarification, then I want to ask a little bit more about that. There was a slide at one point where you were looking at, maybe it was before this, where you were looking at the seismicity rates or the acoustic emission rates. Yeah, can you go back a couple before this one? Because it looked like is there one before this? It looked like this. In two cases, the cumulative number went up and then it just kind of tails off. And maybe is this also related to the point you just made to Joan about the first event has a lot more AE, the first stick slip?
I didn't get exactly what you mean.
Well, so in the 50-degree cut one that you're looking at,
yeah.
So the seismicity, the acoustic emissions, increase and increase and increase until you get the first event, and then for subsequent events, there's very much smaller increase in the number of AE, the rate.
Yeah. Again, let's say that the cumulative acoustic emission curve is different from the first event for the second and the third event. So somehow, yes, I would say that it could be related to the fact that the first cycle includes also some surface evolution that is preparatory and is not included after, because after the fault is already ready, microstructurally speaking.
So it's in, one can focus on that because of these big differences. But then in the next slide, which are you showing us, the first one or subsequent ones for like the 40 and 50?
Yeah, so 40 is this one that occurred after some stable creep on the fault, and this is slip hardening preparatory phase, I would say. Yeah. And this is the third one. Sorry, this is the third one. So it's not the first one.
Yeah, but
because
at this scale, I mean, isn't it true though that you could say that there is a clear change in the seismicity rate as you approach failure? It's just not, there's not a big break in it, but it continues to increase right up until failure, right?
For the
50. Just
yes.
wonder about this idea that, well, foreshocks are not ubiquitous, but there's a clear change in the seismicity rate before this event.
Yeah, indeed. I mean, I agree with you. The point is that the increase, this exponential increase, it's very clear for 40. It's clear for 50, but less accentuated. And for 60 is not detectable. And the main difference between the 50 and the 60 is that in the 60 degrees sample, we have a lot of background seismicity, if we want to call it background seismicity. So I cannot state that foreshocks or precursory seismicity rate increase is not there, but I can say that it's not detectable just looking at the seismicity rate.
Yeah, it's not an obvious big difference, yeah. Okay, thank you very much. Yeah, great talk. Telemaco, go ahead.
Ciao Carolina. Very nice talk. My impression is can you hear me, by the way?
Yes, yes.
Okay, yeah. You very nice showed that you have much more diffuse seismicity before the stick slip in the 60 degrees particularly, right? And that you do not see this increase. So this increase can be not too ubiquitous, but could it be just that you're making this awful damage in the intact rock? I reverse the question. In nature, you may have a damage zone, you may have any sort of minor faults around. Could it be a bias that you're looking at an intact thing? And so instead is a matter of how intact is the rock and not how misoriented is the fault in the stress field?
Yes, this is, I mean, actually, this is a good point. The fact that in the lab, foreshocks activities is kind of ubiquitous is somehow related to the fact that we usually take the simplest system that we know, that is a well-oriented fault in an elastic medium. And of course, if instead of taking an elastic medium, you take a highly damaged rock, you can start to see different things. So yes, I agree with you.